Gabriel. So, forgot to tell you all, Gabriel's videoing these lectures. They'll be posted. They're on YouTube. But we have the camera shows me, doesn't show you guys and gals. So, if you have any problem with this, let me know. But I think it's a useful thing to have these videos up. All right. So as I said, there are binders over there. We're going to be continuing section 6.1, integration by parts. You all saw from yesterday's recitation that there really are no easy problems this first week. I mean, everything's hard, so that you just want to do lots of drill problems so you get to where you can do them in a reasonable amount of time. So today's problems are going to be even harder because they're all going to have twists. So the first problem, the first twist is, who are you? Owen. Okay. The first twist is that we have a definite integral. And you're?
Brendan.
Brendan, okay. So we're missing Zach and Troy. The first twist is that we have a definite integral, but that's not a big deal. You all had definite integrals in Calc 1. We know that we just do the indefinite integral first. But if you were in my Calc 1 class, you know that I often put something on the left here. When you compute a definite integral, what are you computing?
The area under the curve?
Yeah, and in my class I refer to this as the signed area. All right, now remember the approach that we use. We're going to use the fundamental theorem of calculus. To say that what we need to do is we need to find the indefinite integral, and then we need to evaluate that at the endpoints. So we need to find a particular antiderivative, capital F we could call it, or capital I, and we're going to plug it in here. So that brings off, we're going to break out this indefinite integral and put it over here. So we're supposed to find this. And let's give that a name. That's not going to be an area, that's going to be a function. I'm just going to call it capital I of x. Now, I don't know if, did we have any examples on Monday? Let's see, what were our examples like on Monday? Right, so we don't have an antiderivative formula for sine inverse of x. If we did, then this wouldn't be in the integration by parts section. But we do know how to find the derivative of sine inverse of x. So we should think of this in a way that we end up, instead of having to find an antiderivative of sine inverse of x, arrange things so that we're going to find the derivative of sine inverse of x. So we're going to do a trick. We're going to write this as sine inverse of x times the number 1. So that's another complication. It's an integration by parts problem where you don't actually start with two terms. So one thing you can do is you can do this trick. And so we're going to think of this as an integral of f g prime. And by the integration by parts formula, this is f times g minus the integral of f prime g. So there's our first thing to review. Or not review, to put as a reference. Remember that integration by parts tells us that the integral of f g prime is equal to f g minus the integral of f prime g. Remember, there are binders over here. Okie doke. Well, let's do the integration by parts details. I'm not sure how much room we need for this problem. So we have our f of x, which is sine inverse of x, and we have our g prime of x, which is the number 1. And according to this, we're going to need f prime, and we're also going to need g. All right, raise your hand if you know one of those things. Marcy.
Antiderivative of 1.
Okay, what's that going to be?
X.
X, all right. Now, somebody else. Raise your hand if you know f prime. What's the derivative of sine inverse of x? Oh, you got. Let me call on you, please. So raise your hand if you know the derivative of sine inverse of x. Yeah.
1 over the square root 1 minus x squared.
Are you sure?
Yes.
Cool. Anybody want to second that? Liam, you're looking away. So what do you do if you don't remember this, or if you remember it but you're not sure? I mean, you're sure, but you're the only one who's sure. Yeah. What?
Is there like a derivative rule we can use?
Yeah, let's see if we can figure it out. So we were thinking this is going to be 1 over square root of 1 minus x squared. But how do we remember this, or how do we verify this? Well, more stuff to remember. Remember that the inverse function rule says that if I have a function called h, and I have the inverse function, and I'm finding its derivative, I have to do this. I have to do 1 over h prime of h inverse of x. So that's a formula from the deep dark past. So let's figure this out. This means that the derivative of sine inverse of x is going to be 1 over sine prime of sine inverse of x. Now raise your hand if you know what sine prime is. The derivative of the sine function. Good. So this is going to be 1 over cosine of sine inverse of x. Now how do we figure that out? Well, remember what this means is sine inverse of x means the angle whose sine is the number x. We're supposed to think about that angle and figure out what its cosine would be. So we want to draw a picture of an angle whose sine is the number x. So here's a picture of an angle whose sine is x. Sine of theta is opposite over hypotenuse, so it's going to be x over 1. So it's going to be x. So that means that theta is sine inverse of x. And we're supposed to find cosine of theta. So help me out here if you can tell me how do we find cosine of theta? Your hand is half up. Yeah, that's the closest we had. Well, in this picture, how do you find?
We have to use a Pythagorean theorem, but just for variables.
Yeah, cos theta, remember, is the adjacent side over the hypotenuse. What's the length of that adjacent side?
It's 1 minus x squared, right?
Square root. Because this squared plus this squared has to equal 1. So square root of 1 minus x squared over 1. So just square root of 1 minus x squared is the cosine of theta. Oh, so that's what I got to do here. This is 1 over square root of 1 minus x squared. Good. So this formula is right. So there's all sorts of stuff to review in this first week. So remember what we did on Monday. We thought of this as a pair of terms in a yellow circle. That's going to be this pair of terms. And a pair of terms in a red circle. That's going to be this pair of terms. And so this is going to be sine inverse of x times x minus the integral of 1 over square root of 1 minus x squared times x. Yikes. Okay, so we broke off from the main problem to do the indefinite integral details. And that involved integration by parts, but we're not done. So we need to break off again because this is too much to do right here in line here. Let's do a substitution problem. Over on this board. Oh, Gabriel's office hours are Monday, Wednesday, Friday from 1 to 2 in Morton 423. All right, so our problem that we need to do is that substitution problem. So we have to compute the integral of 1 over square root of 1 minus x squared times x, and there's a dx there. Now, why is this a substitution problem? Well, I mean, in general, you try a bunch of stuff, and at some point you realize, I'm going to need to use substitution. The clue is that we have a nested function. And so we have to get a new version of the inner function. We're going to simplify this integrand by finding a new version of that. So 1 minus x squared, that's going to be our inner function. I'm going to call that w. You're used to using the word u substitution, but in this chapter on integration by parts, so this section on integration by parts, you're often using u's and v's for the integration by parts stuff. So I want to use a different letter for the substitution stuff. So we've got a new version of that. And then if you had me for Calc 1, you know that the next thing I do is I find a new version for the dx. Well, dx is going to be 1 over w prime dw. We learned this the way to think about this is that w prime is equal to dw dx, and if you multiply both sides by dx and divide both sides by w prime, you get this. It's not really multiplication, but it's the way you can remember this. So we're going to have a new version of that red term. So the first thing we do is we substitute in those things. We don't deal with anything else. We just see what happens when I substitute that stuff in. 1 over square root of w, and then I have an x, and then I have 1 over w. Oops. This, I didn't finish this. W prime is 2x, so this is minus 1 over 2x dw. So that's what my dx is. So here I put minus 1 over 2x dw. So I substituted in that green stuff for the green w, or for that green term, and I substituted in all this red stuff in place of that dx. So that's the substitution step. Now we do the cancellation and simplification. Notice there's an x in the numerator, and there's also an x in the denominator. And then there's a 1/2, which I can bring out front. So the x's cancel, and I end up with this. All right, well, that can be simplified or put in power function form. And we can use the power rule for integrals. So minus 1/2 times w to the minus 1/2 plus 1 divided by minus 1/2 plus 1 plus c. So minus 1/2 plus 1 is 1/2. So this is minus 1/2 times w to the 1/2 divided by 1/2. Okay, well, dividing by 1/2 is the same as multiplying by 2. Those 2's get together and have a party. They cancel each other out. So I end up with minus w to the 1/2. So in other words, minus square root of w. But now I have to substitute back. Minus square root of 1 minus x squared. So all of that stuff is the substitution problem. It says that this integral here is equal to this. So we have that blue integral is going to go, the result of that is going to go here. So I have sine inverse of x times x minus, you got to keep track of your minus signs, minus a minus square root of 1 minus x squared. Now let's simplify this. This is equal to sine inverse of x times x plus square root of 1 minus x squared. That, all that junk, was my side calculation of this indefinite integral. So I'm going to put that back in here. So what I have to do is I have to do that function, sine inverse of x times x plus square root of 1 minus x squared, and I have to evaluate that from 0 to square root of 3 over 2. So like I said, there are no easy problems this week. They're all hard, every one of them. Let's keep going. So we're still computing the definite integral, so this is still the signed area. So we have to take that mess, sine inverse, and we plug in square root of 3 over 2. And then we multiply that by square root of 3 over 2. And then we add square root of 1 minus square root of 3 over 2. That thing squared. That's that whole mess with the square root of 3 over 2 plugged in. And then we have to do more. We have to substitute an x equals 0. So sine inverse of 0 times 0 plus square root of 1 minus 0 squared. Okay, let's work from the right. 1 minus 0 is the number 1. Square root of 1 is 1. So I get plus 1 here. Sine inverse of 0 is 0 because sine of 0 is 0. Doesn't matter because it's being, it's got a 0 next to it anyway. Now let's go over here. Square root of 3 over 2. When I square that, I get 3/4. 1 minus 3/4 is 1/4. Square root of 1/4 is 1/2. So this is 1/2. I'm going to let you, write that down. If you don't like it, you can work that out after, on your own. Now, what's sine inverse of square root of 3 over 2? Raise your hand if you can help me with that. Oh, you tricked me. I thought you were going to raise your hand, but instead you just did this. But do you know? What's sine inverse of square root of 3 over 2? If not, how would we figure it out if you can't remember? Liam?
It would be sine of x equals square root of 3 over 2? Or x
Yeah, it'd be the angle whose sine is square root of 3 over 2. What angle is that?
It's part of a 30, 60, 90 triangle, right?
Yeah, or let's use the unit circle. Because you should, so, here we have pi over 6. Here we have pi over 4. And here we have pi over 3. Those famous angles. And this is the angle of 0. And this is the angle of pi over 2. If you want to save money on your tattoo, you can just get this part of it tattooed. So the key thing is, what are the coordinates of these points? This is 1, 0. This is square root of 3 over 2, comma 1/2. This is 1 over square root of 2, comma 1 over square root of 2. This is square root of 3 over 2, comma 1/2. I'm sorry, this is 1/2, comma square root of 3 over 2. And this is 0, 1. So when we're asking for this value, what point on this unit circle are we interested in? Marcy, come up and color it red.
Can I just say it?
No. This is like the 7th inning stretch. So what's the point that we're interested in here?
You said sine negative that.
Yeah, huh?
Sine.
Which point are we interested in?
Would not be this one?
The point on the graph, on the circle that we're talking about. Yeah, that's great. Thank you. You can count. You can get to, if you're logging your steps, you got some steps there. So the thing is, the sine of the angle is the y coordinate. So the angle whose sine is square root of 3 over 2. Well, that's going to be the angle that corresponds to this point on the unit circle, and so that's the angle pi over 3. Pi over 3 times square root of 3 over 2. So this is now square root of 3 divided by 3 is going to be 1 over square root of 3. And so I have 1 over 2, I have pi over 2 square root of 3 and minus 1/2. There is my answer. Now we can go to helpmecheatonmycalculus.com and see if that is right. So what was our original function? Sine, so arc sine. So let's do the indefinite integral first. Our indefinite integral we figured out was sine inverse x times x plus square root of 1 minus x squared. Let's see if that part's right. Yeah, there we go. There's that function right there. Now let's turn this into a definite integral. Let's go from 0 to square root of 3 . And that's the answer we got. Pi divided by 2 square root of 3 minus 1/2. Now you have to be able to do some arithmetic if you want to compare your answers to that and see that we got the right answer. So in this problem we had to do a trick we did integration by parts. We forced integration by parts by forcing there to be a times 1 in here. And then we had to do substitution. Now, this next problem, notice it would not have, there would have been nothing to substitute here. We didn't have a nested function. So we forced ourselves into the integration by parts world, and then a substitution problem emerged. Now let's think about this problem. Let's find the indefinite integral of arctan of 11x. Now, we're computing an indefinite integral, so I'm going to put a thing on the left, a label for this. I'm going to call this my I of x. So notice, there are not two terms here. There's only one term. Yeah?
So if we write the inverse tan side time instead of arctan?
I'm going to use both because you'll see both in the book. So sometimes one, sometimes the other. Yeah. So the question was, why not write tan inverse of x, 11x? So because you just want to write both sometimes. All right. So we don't have integration by parts staring us in the face. We only have one term. So, but we know we could force our way into that situation by doing this kind of trick. But also we can see a complication right away. There is a nested function. So let's deal with that first. Let's simplify this by doing a substitution. So So we'd really rather not have a nested function. So let's figure out a new version of the 11x, and let's figure out a new version of the dx. So the 11x, we're going to just call that w. So we're going to have a new version of the 11x. And then the dx, well, that's going to be 1 over w prime dw. So that's going to be 1 over 11 dw. So that's going to be our new version of that red dx. So we're going to have the integral of arctan w. There I did my green substitution. And then I'm going to multiply by 1 over 11 dw. There's my red substitution. And that's cool because that 1 over 11 comes out. So we no longer have a nested function. All right, now, we can force an integration by parts. Question is, do we want, by doing this kind of thing, we can just stick a times 1 in there. Now, do we want to stick it on the left or on the right? Well, I keep the left function to be the f, the thing that's going to be differentiated, and I keep the function on the right as my g prime, the thing that I'm going to integrate. Well, I don't know how to integrate this thing. I know how to take its derivative, so I'm going to make that my f. So in other words, I'm going to keep that on the left. Arctan times 1 dw. And then remind ourselves of the form. This is the integral of f times g prime dw. And so by integration by parts, I, b, p, I'm going to do this. I'm going to have the 1 over 11 out front, and I'm going to do f g minus the integral of f prime g dw. Okay. So let's do the integration by parts details over here. We have our f, which is arctan of x, and we have our g prime, which is the number 1. So our g is going to be an antiderivative of that, which is not going to be 1, it's going to be w. And this is not arctan x, it's arctan w. So now the question is, what is f prime? What's the derivative of arctan? Yes. Anybody want to quickly review why that works? It's the same kind of thing. Well, yeah, let's do it. Let's review why that works. So over here we should have things that we remembered. So the derivative of sine inverse of x is 1 over square root of 1 minus x squared, and the derivative of tan inverse of x, or derivative of arctan x, is 1 over 1 plus x squared. Let's see why that's true. So remember that the derivative of tan, tan inverse prime of x is 1 over tan prime of tan inverse of x. That's the inverse derivative formula. So this we got to figure out, but what's tangent prime? Nope. Secant squared. So this is going to be 1 over secant squared of tan inverse x. So in other words, 1 over secant of tan inverse of x, that whole thing being squared. Okay, well, let's draw a picture of an angle whose tangent is x. Who can help me do this? Great. So, thank you. So, tangent of theta is x over 1, which is just x. So that means that theta is tan inverse of x. So what's secant of theta? in this picture? How do you compute secant?
It's 1 over cosine theta.
Yeah, 1 over cos theta. So that's 1 over the adjacent over the hypotenuse. So in other words, it's going to be the hypotenuse over the adjacent. So whatever that length is, divided by that length. What is this length? Marcy?
1 plus x squared?
Square root of that. Yeah, square root of 1 plus x squared. So this is going to be square root of 1 plus x squared, all divided by 1. So in other words, just square root of 1 plus x squared. Okay, so that's what goes in here. 1 over parentheses, and inside the parentheses, square root of 1 plus x squared. But then that whole thing gets squared, and I just get 1 over 1 plus x squared. So good. This is true. So I use those details, and I get 1 over 11 times f arctan w times g, which is w, minus the integral of 1 over 1 plus w squared times w. It's a real bummer how hard these problems are. Because here we have a substitution problem. Let's go over to the sideboard and do the substitution problem. No, I guess I'll just do it up here. So the substitution problem is the integral of 1 over 1 plus w squared times w. So the reason this is nested is because, well, one way to think of it is it'd be great if the thing on the bottom were not a whole expression, but were just a single character. So let's think of that as our inner function. We're going to get a new version of that. 1 plus w squared. Well, let's call that y. I don't want to use other letters that get used for other things. So that's my inner function. And remember, the method that I use is that I also find a new version of that. So dw, remember you build this as 1 over y prime dy. So that's 1 over 2w dy. That's my new version of that red circle thing. So I make that substitution. I leave that. I don't worry about that. I just hope for the best. And I get 1 over y. And then I have that rogue w sitting there. And then I have 1 over 2w dy. So I made my green substitution, replaced that green term with that green y. I made my red substitution, replace that red dw with all this red junk. Now notice, those w's get together, they have a party, they cancel, and I have a 1/2, which comes out front. So I end up with 1/2 times the integral of 1 over y dy. Now, who can tell me what's an antiderivative of 1 over y? Yeah.
Is it the natural log of y?
Almost. What do I need to do? Slight change. It's not natural log of y, it's... Exactly. Thank you all. So 1/2 ln of absolute value of y plus c. Okay, now we substitute back. So this is 1/2 ln of the absolute value of y, which is 1 plus w squared plus c. So absolute values are a pain. I think we can all agree with that. But you know that if you know something is not negative, then its absolute value is the same as itself. So like the square root of 7 is 7. Square root of 0 is 0. But if something is negative, like square root of negative 5, the way I get its absolute value is I have to multiply it by negative 1. But if I've got something that I know is not going to be negative, then I can just get rid of the absolute values. Well, look, w squared is going to be greater than or equal to 0. So 1 plus w squared is going to be greater than or equal to 1. So this will be greater than or equal to 1. So I can just get rid of those absolute value signs. So I have 1/2 ln of 1 plus w squared plus c. Now I just need a particular antiderivative, so I'm just going to use the ln term. So when I bring that stuff back in over here, I have 1 over 11 times arctan w times w minus 1/2 ln of absolute value of 1 plus w squared. So all of this work here in this big blue circle was here. But this is still a substitution problem. Dang it. So w is 11x. So this is 1 over 11. So we're going to substitute back. 1 over 11 times the quantity arctan of 11x times 11x minus 1/2 ln of 1 plus 11x squared. I hope this is right. So this is, on this term, the 11s get together. I just end up with arctan x times x. But when I hit 1 over 11 with this term, I end up with minus 1 over 22 times ln of 1 plus 121x squared. I think that's right. Let's see. I'm not going to show you in case it's wrong. Oops. This is supposed to be 11x. So let's see. So there's our x arctan 11x term over there, and then minus 1 over 22 ln of 121x squared plus 1. So again, this is a bummer. I had to do a substitution problem to make it a little bit easier in the beginning, and then I had to do integration by parts, then I had to do another substitution. It's really a bummer. These problems are hard. I could have maybe gotten away without one of the substitution problems and just attacked this one as an integration by parts problem right away. It would have just made my derivatives. I like taking the derivative of arctan x. I wouldn't have liked to take the derivative of arctan 11x. All right. We go just like 8 more minutes, right? So that's enough for me doing whole problems. What I want to do now is I want to talk about a killer problem of a sort that you have on your homework. And I want to talk about strategizing. These problems are also problems that are similar to ones you have on your homework. Well, let me double check attendance. Did Troy or Zachary show up? Okay. So the last problem I want to talk about is, I just want to talk about this setup. So the integral of 5 e to the 7x, 5x e to the 7x over 1 plus 7x quantity squared. Now this is just, let's simplify it right away by pulling the 5 out front. So the last couple of problems that we did today, the first two examples that we did today, we had to force ourselves into doing integration by parts by just putting in that number 1 and using that as the g prime. We didn't really have a choice. But here we have difficult choice. There's no obvious yeah.
This is technicality and should have some dx's.
That's why Gabriel's paid the big bucks. Thank you. Because everybody will, if you had me for the fall course, you know I'm a stickler for details like that. So thank you. Especially when you end up doing substitutions. You have to pay attention to the dx's and the dw's and the dy's. All right, so there's no obvious f g prime here. So let's just think about, so we have just 6 minutes. Let's just think about some choices that we could make for f and g prime. But don't go very far. Let's try f being e to the 7x and g prime being x over 1 plus 7x squared. Okay, well then f prime would be 7 e to the 7x. Notice that's no simpler. And what would g be? G would be this integral, x over 1 plus 7x. And I don't know. That's not a good problem. So, you know, if I do my trick of having this yellow term, which I don't know how to do that integral, and then having to integrate something else, it's going to be hard. So, nope. Let's try the other way around. Let's try f equals x over 1 plus 7x squared, and g prime equals e to the 7x. Well, in this case, f prime is going to be ugly because, you know, you use the quotient rule and you're going to have bottom squared, so you're going to have something even uglier than this. And what's g? Well, g is going to be e to the 7x over 7. And so when I do my trick of these two things being multiplied together minus this integral is going to be even uglier than the integral that we started with. So, nope. Well, there's a really cool thing here. Let's try this. Let's try f equaling x e to the 7x. And let's try g prime equaling 1 over 1 plus 7x squared. Well, f prime, if you use the product rule, you get 1 plus 7x e to the 7x. Oh, that's interesting. A 1 plus 7x emerges. Now let's figure out what g is. This is 1 over this thing squared. Now if you did it, you do a substitution problem, and I think you can see, if we're playing a board game and you would get penalized and if you challenged me and you were wrong, you wouldn't want to challenge me because this is going to look pretty believable. Let's check. Here I've got 1 over something, so something raised to the negative 1 power. When I take the derivative of this, I'm going to get that thing raised to the negative 2 power. So it's believable that the derivative of this is this. So it's believable that the antiderivative of this is this. All right, well, what would we be doing with this then? We'd be doing our trick of multiplying these two together and then taking the integral of the product of these two things. Now look at that. The product of this and this, the 1 plus 7x's are going to cancel. So it's going to be a really easy integral. It's amazing. It's wonderful. I mean, you would never think of pairing these two together as the f. But, you know, when I tried this, this is not what I tried. I tried one of these, and I kept thinking, well, this is way too hard. So this is the way these problems go. They're all hard, and B, you end up with some dead ends. All right, let's stop there. So Zachary and Troy are not here. Remember, there are binders here in the front of the room. If you looked at Monday's video, you'll discover that there's no sound. At some point, I might try to redo Monday's video, but this video should have sound. Gabriel's office hours, remember, 1 p.m. to 2 p.m. today. Thanks, Gabriel.